Hello, everyone. It's Michael Shermer, and it's time for another episode of The Michael Shermer Show. This one's brought to you by Wondrium, a series of college-level audio and video courses and documentaries produced and distributed by The Teaching Company. Wondrium brings you engaging educational content through short-form videos, long-form courses, tutorials, how-to lessons, travelogues, documentaries, and more, covering every topic you've ever wondered about, and many you probably never even knew you were wondering about until you saw the list. So what you do is you just subscribe. The offer through this show this month is you get, if you subscribe for 1 year, you get 2 years. That is, you get a free year. So why would you not do this? It's a great deal. You get just endless content. You just download the app and you're off and running. Here's one, for example, that I'm using this week myself, called Assessing America's National Security Threats. This is a new one that they just released. Here's a sample of some of these 12 lectures. They're 30 minutes each. Well, 20 minutes each. Actually shorter. Oh, good. I can just blast through these, probably do the whole thing in maybe 2 bike rides or two drives. From Cold War to Hot Wars, Vladimir Putin's Russian playbook. Well, that's rather relevant now, isn't it? Understanding China's Communist Party, also rather relevant. Afghanistan and jihadist terrorism, still a problem. Iraq and the Middle East, still a problem. You get the idea here, just kind of scanning down. Climate change and energy security. Dangers in space and cyberspace, the new information warfare, building strategic confidence, and learning from dereliction of duty. That should be a curious one. Anyway, so you just access the app on your phone and just scroll through all the different courses. There's hundreds and hundreds of them. It's just phenomenal. I mean, just look at that. It's just amazing. Just touch on it, boom, up pops these all the lectures. And you can stop at any time, skip courses, skip lectures within a course, and it remembers where you were located. Anyway, I'm just kind of riffing here because I love the product so much. So check it out. If you do it through this show, you get 2 years for the price of one. Go to wondrium.com/Shermer, WONDRIUM.com/Shermer, and you're off and rolling. All right, check it out. Thanks for listening. All right, everyone, it's time for another episode of The Michael Shermer Show. It's me, your host, Michael Shermer, the publisher of this Skeptic magazine. Here we go. This is our new design, latest issue out this week. The 4th issue of the year. We are a quarterly publication devoted to investigating claims of the paranormal, pseudoscience, fringe groups, and cults, and claims of all kinds, including junk science, voodoo science, pathological science, bad science, non-science, and plain old nonsense. And unless you've been abducted by aliens and been on Mars, or you went with Elon Musk, there's a lot of it out there that is bunk. And so even though we don't like being called debunkers, there's a lot of bunk out there. That's part of our job. We also look at how science works and promote science and critical thinking and rationality. And to that extent, my guest today is a physicist, Susie Sheehy, an accelerator physicist, not a particle physicist, an accelerator physicist, which a term I hadn't heard before, so we'll have to explore a little bit of that. She's also a science communicator and academic who divides her time between research groups at the University of Oxford and the University of Melbourne, which I think she's at today, right, Susie?
Yeah, I'm in Melbourne at the moment. Yep.
And Melbourne, yep. She's currently most focused on developing a new particle accelerators for application in medicine. And this is her new book. It's called The Matter of Everything. I love that title. It has that kind of dual meaning. How curiosity, physics, and improbable experiments change the world. I think this is the U.S. cover. I think the UK Australian cover is slightly different.
Here you go. There's the UK Australian one.
Oh, there we go. I like that. Okay,
and a slightly different subtitle as well. Yeah.
Yeah. Why did they do it? Well, at least they don't change the title, which confuses readers. Oh, she has 2 books. No.
One book.
Yeah. So great. It's great to have you on here. Let's get right into it. Before we dive into the book, though, just give us a little bit of background about yourself. I'm always interested in this show on how lives turn out, a combination of genes, environment, and luck. I see you have a identical twin sister.
Yeah.
All right. So talk a little bit about your family background and how you got into what you're doing and what your sister does.
Yeah. It's I was born and raised in Australia, and then eventually, after studying my degree, I moved over to the UK where I did my PhD and started my research career. And then I've just recently, in the last couple of years, actually moved back to Australia to bring my research field home. But yeah, I grew up literally on the edge of the desert for the first couple of years of my life in a place called Mildura, and then moved, to the biggest city for education. But yeah, my identical twin and I were always very curious people, always asking big questions about the world. And when it got to our university studies, I studied a science and engineering degree while she studied an arts degree. So effectively, we were both asking big, interesting questions about the world. We just went through very different routes, and we sort of diverged for many years in our 20s, And then as we sort of reached our 30s and matured, you sort of realize actually how much you have in common. And just the ways in which we ask questions about the world can look different. And so to my surprise, she came around as being really interested in science, and I came around and being quite interested in what she does, which is more in the sort of history, philosophy, and even mental health space.
Interesting. Yes. Okay. And is it just the two of you, or do you have other siblings?
Oh, we have one brother who's a year older as well.
Mm. And your parents, are they educated? How did they bring you up in terms of getting you interested in science or whatever?
So my dad was a maths teacher, high school maths teacher, though we didn't exactly sit around and do maths at home, right? Except for, and I do tell people this is the one exception, in my house it was normal on Christmas morning to have to answer maths questions, like little maths riddles, before you were allowed to open your Christmas presents. I think he only tried that 1 or 2 years. Because it became obvious that my sister was not interested. I mean, she was good at maths, like she was good across the board, but she was just like, this is ridiculous. Whereas my brother and I were both a little bit more, mathematically interested, and so we would get all the presents first. So it didn't really work.
That's really funny.
And then my mum did a bunch of different stuff. She was a teacher. She was a homemaker. She helped them run a small business. So eventually they ran one of the first internet service providers in Australia, which is little mum and pop business. So they did all sorts of things, from sort of that more academic math side of my dad through to the more entrepreneurial. So I guess I had that background. And because of my dad's sort of interest in computers, our dining room table was just covered in computer parts when I was growing up. So we didn't have that many sit-down dinners around the table, but like I was surrounded by technology and really the nuts and bolts of it, not just sitting in front of a computer. But when I got my first computer in my teenage bedroom, I had to build it myself. So we did have that influence growing up.
That's really funny. And did you have, by chance, you don't happen to know why it's called maths in the UK and Australia, and in the United States it's just a singular math?
Well, I mean, the full word's mathematics, right?
Yeah, so they just
I guess it's just
as math.
how you contract it.
See.
That's my guess.
Yeah. And did you have any mentors or teachers that kind of nudged you into the physical sciences? And here's why I'm asking. Let me just tee this up for you. As you know, there's a big debate about why there aren't more women in STEM fields, although there are in medicine and biology and most of the other sciences. And so is, the two hypotheses on the table as well. There's still some misogyny and so forth in the physical sciences, but not so much in the other sciences, I guess. Or maybe women get nudged away from those fields in middle school or something like this. And so, it's more of a pipeline issue. There's just fewer applying for the jobs because there's fewer that get graduate degrees, because there's fewer that get undergraduate degrees. There's fewer that go into it in high school and so on. And, so what are your thoughts on that, and what nudged you in that direction?
Yeah, so I mean, obviously I've done a lot of reading and thinking about those issues of women in STEM, being one myself who sort of end up having to learn it. But, that's not my area of expertise. I should be clear, is because this is, an academic field of research, is why we get this gender disparity in these certain fields. So my understanding is it's a little bit of both of those hypotheses that you put forward, and perhaps some other factors as well. And it's a lot of that sort of overall societal influence of whether or not someone grows up, first of all, interested in being exposed to something and building what they call science capital. So like repeated exposure to science in a positive way. And in this case, I guess with the physical sciences. But then, if you think about how you end up becoming or doing anything in your life, you've also got to feel like you belong. And this issue of belonging is one which I've struggled with in my career, because even even in my field today, it's sort of about 10% women. And the further you go up in the ranks, the fewer women there are. So it's interesting. It's interesting to reflect on it in that statistical way. So sometimes I find that individual sort of anecdata, as it were, like my individual anecdote might not be that useful. And I actually think the people that would be most useful to talk to is the women who perhaps had an interest and then didn't pursue it as a career. So, for example, my sister did physics to the end of high school, but she didn't pursue it as a career. And I would say, like in her case, it's probably because there were just other things that grabbed her more. But if you look in the literature, it may be that also society told her in a way that other fields were more fitting, or she would find more belonging in the sort of philosophy or history fields that she ended up studying and then moving into. She's a museum director today. Whereas I guess in my case, one of some of the factors that I feel I was lucky with was I did have some good teachers who would, set little, even in primary school, set little challenges that, little engineering challenges and things where I think I won a piece of circuit board when I was in like grade 3. I don't know, how old are you then? Like 7 or 8. And that was like my pride and joy for a while, that I'd won this piece of green circuit board. I didn't understand how it worked, but I won it. And then, so lots of extracurricular stuff I had. And I guess I also had that influence at home of like things like math in your case, being normalized, like, and being good at math, not being something to be ashamed of as a woman. And then I also my sister and I both went to an all girls sort of high school, or like through to the end of school. And so that also meant that I never received the societal message that physics wasn't for women. And I remember when I got to university and there was like a women in physics group, and I remember thinking, but why? Like, I know there's few women, but I'm just a physicist. Why would I just want to be a physicist. Why would I self-identify or pigeonhole myself as a woman in physics? And it's only as I've gone on and understood the barriers faced both now, but also obviously historically, which I write a bit about in the book, that I've understood why it is that we might need, groups like women in physics groups where, people who've had similar life experience and similar challenges can actually connect with one another and feel that sense of belonging, which is one that we don't talk about much in the literature. It's not talked about much. But in my experience and the experience of a lot of the women that I know, and I guess, again, anecdotal, right? But that felt sense and that emotional sense of how it feels to go into work every day is so important. If you go in and every day is a challenge, and then you have other challenges in your life, and especially when you reach, sort of the mid-30s and older, like people have kids, they have caring responsibilities for parents and other people, they have all sorts of things going on. And then when you face also with challenges like biased funding systems and biased reviews and women getting less money and less likely to be promoted and less, you just go, why bother, right? Like at some point you're like, how much passion do you have to overcome that? And in that sense, I'm not the right person to talk to because I stayed, right? So we should talk to some people who left and sort of say, right, what, like, how do they feel about that? And I'm sure there's been studies that have been done where women were interviewed, but we'd have to dig them out.
So yeah, in social psychology, it's called social proof, where you look to others to confirm your hypothesis about whatever. Just what should I do in life, or should I believe this or that, and so on. And we do depend on others. So social capital, social proof. In that sense, role models could make a difference. Like we just got our first United States Supreme Court justice who's African American woman. And, much ballyhoo was made about this. Biden came right out and said, that's what I'm going to do because that's what I'm going to do. It's good to have a role model. And there was just a ton of social media commentary about, yes, now I can look, these young black women, I can look out, I could do that because I can see somebody who also did it.
Yeah.
So there's apparently a pathway. Did you have anybody like that? Teachers, mentors, somebody that said, hey, just go for it. You can do it.
So I would say smaller influences rather than like one individual where I was like, wow, that person is who I want to be. In high school, I had a really great teacher in my final year of high school. We do this, what's called specialist maths in Australia, which is like well known to be the hardest subject in the whole of school, right? And she was just incredible. And just watching her solve problems on the board, like just on the fly, and just really use her brain and not be ashamed of using her brain and being a smart person, and also not being afraid when she didn't know how to do something, even though she was the teacher. Uh, and then she'd work her way through it and she'd get to the answer, and she'd also be able to sort of sense check and be like, oh, wait, that's not right. I must have made a mistake, and go back and check, and also not be ashamed about that, right? To just see a smart woman working was quite inspirational to me. And then I think most of the other influences that I had in my early career and mentors and even my PhD supervisor, they were all men. But that intellectual connection and that passion for the subject and those things, that sort of led me through and got me interested on a human scale. And at that point, the gender aspect didn't matter. I think then later in my career, it became more important, because I think for the first 7 years of my career from PhD onwards, I didn't have a single direct female colleague. And after a while, that really became a drag.
Yeah.
So then at that point, I cultivated a sort of online community at first. At first, I only knew these women online, and now I know a lot of them in real life. Just friends, basically, who were also doing a similar thing in life, similar research areas, or women who were perhaps combining their research with the science communication, which is what I was doing as well. And it's been a real pleasure to follow their careers and, sort of peer mentor each other. I think some of the traditional, especially sort of in physics, role models, I mean, the one that always comes to people's minds is Marie Curie, right? I gotta say, someone who's so work obsessed and killed herself with her own research is
Right.
not quite,
No. That's funny.
like not quite the role model that I'm looking for in terms of balance. Of course, what she achieved is incredible, but I think sending the message that you have to be this indomitable woman who, just through sheer force of will makes it sends a really bad message to younger people, I think, and to me, because it's like, well, I feel exhausted already. If the message is that I have to push and push and push more than everybody else around me, even though academic research, of course, is a very competitive field in the first place. I mean, just, you can sense my exhaustion just even thinking about it.
Yeah, it's like, who would want to be a CEO of a Fortune 500 company? There's more men than women. But who the hell wants that job anyway? And, like 80 hours a week, you have to work for most of your life. You have no family life. You're not much of a parent, much less a spouse.
Yeah.
I don't know.
And
maybe I'm overgeneralizing a little bit, but yeah, I get your point. Let me just register one more hypothesis, and that is just vocational interest differences between men and women that appear to start diverging fairly early on, like maybe early middle school, something like that, where they start giving students vocational interest tests. Just what are you interested in doing when you grow up, kind of thing. And there are differences, just roughly over two overlapping bell curves on average. Women are more interested in people, men are more interested in things. So this is the hypothesis that STEM fields have to do more with things. So you're going to get more boys and then men kind of diverging down that path. Just like in medicine, there's, for whatever reason, there's more women in pediatrics and OBGYN and so on, more men doing plastic surgery or, that kind of surgery. And that pays more. So you see these kind of vocational income differences or salary differences or whatever. But it may be in part a function of what actual job you're doing, right? So that may stem from just vocational interest differences, not intellectual differences. Clearly, there's none. All the research on cognitive psychology on cognitive gender differences in cognitive abilities. On average, men and women are the same intellectually, and women are better at some particular subsets of the IQ test and so on. Men are better at others and whatnot. But that's only part of it. It's what do you want to do? Remember the first time I went to an amateur astronomy group, it was all guys. I'm like, this is boring. Where's the women?
Yeah.
And it's not like they didn't want women. It's just there weren't any there. It's like, oh, man.
Yeah. Oh, look, there's so much to unpack in something like that, isn't there? In a hypothesis like that. I've done a lot of reading around these issues because I also got to a point in my career where I really was like, actually, is there a difference? Like, what does the research say on this? So there's a couple of books that I read that one was called Pink Brain, Blue Brain, and one was called what was it? It's one of Cordelia Fine's books.
Oh,
I can
yes.
send them to you for the show notes.
Yeah, no, I know that. I know that. Yeah.
And so what I've come to understand through that is that this supposed difference, the difference is real, right? Like you can measure the difference in what someone ticks on a survey and what they're interested in. But where that difference comes from, as I understand it, a lot of people have assumed over time that there's somehow that this is based on gender and biology, which according to all the stuff that I've read anyway, and the research that people have shared with me, and this is obviously a very active topic, I mean, there doesn't seem to be much evidence that there's a genuine biological basis. When you go way back into sort of early childhood studies, our biases as adults influence kids, even very young kids, so strongly. Like they do these tests where they put babies in a room with different types of toys. And when the study was originally done, I think it was something like they found that the male baby, I mean, gender isn't even a binary, right? But okay, but if you take the male babies, they seem to go more for the things and the sort of but apparently they failed to take into account the like facial expressions and the behavior and the body language of the researchers or the parents who were in the room with the babies. And babies, I mean, they pick up such subtle cues, right? They're little sponges that pick up, little every little thing that we do. And so as I understand it, when that research has been reviewed and gone back over and checked how it was actually done, the conclusion from that is that it's very weak evidence for this difference, and that it's, the hypothesis that this comes from the social cues given by the researchers and the parents involved in the study could easily be the reason. And so it's sort of not at all clear that there's any, as I understand it anyway, that there's any true basis of that being a gender difference, which then you sort of go, okay, then the historical, cultural, societal factors start to look a lot more like the issue. And this has been borne out a little bit in interventions that people have made to try and improve the uptake of girls in particular in subjects like physics. The one study that really had a really good impact in that area and actually genuinely increased uptake found that you have to do an intervention across the whole school, across every subject, all the teachers, all the parents, and all the kids, in order to actually improve the uptake of a subject like physics. Because if you think about it, a lot of people, and I experienced this even, the influence of being told that something is not right for you or is not for women, for example, often doesn't come from that subject area of study. Like physics teachers are like, anyone who's interested, come and study physics. It's for everyone.
Yeah.
But you sit in your English or history class and the history teacher might be like, oh, I could never do that. It was too hard for me. I wasn't cut out for that, for example. And that can send a message that, oh, maybe it's too hard for me too, because I identify with you as a woman, for example. So they found this one study in the UK basically found that to improve the uptake actually needed education and training and intervention across the whole school. So that indicates to me that it's more of a societal influence than anything else. And that's what I've sort of come to experience. But that's about all I can say on it from the studies and things that I've read,
that's
because
right.
it's such a detailed topic, and as a sort of, it's not my research area, so
yeah.
But it's an interesting one.
Those. Yeah, and I'm familiar with some of those experiments. I'm told that by my evolutionary psych guests I've had that you can even do this with chimps and baboons. The little baby males and the baby females play with different toys. How are they influenced by the experimenters in the room? That's a counter to that. Also, though, all we want is that everybody has equal opportunity. No obstacles, either subtle, social, or legal, or whatever. And then just let the chips fall where they may. I mean, it doesn't have to be 50-50 exactly. Or if you want to talk about race, has to be, whatever percentage of the race is in the population. Just lower the barriers and let people do whatever they want. There was that study in, I think it was Sweden, where they kind of the most liberal, tolerant, who are trying to, increase the percentage of women in STEM and so on, and racial groups and whatnot. and they still have differences. So it could just be vocational interest differences, that maybe it's 3 or 4 things operating at once. Social science is so difficult because there's so many causal vectors interacting at the same time. It's hard to control for them.
I find those ones interesting because, when you get to that high socioeconomic status and high gender equality in particular in countries like some of the Nordic countries, you still do see this difference. I agree. So I want to point that out. And that's an interesting one because when I've discussed with people in those societies, their understanding of it is the fields themselves, like STEM fields themselves and STEM jobs, have a certain culture, right? There's a certain working culture that might look different between, and this is something my sister and I have experienced, like the culture of her workplaces and sort of the arts and history and museums, and even the way that people interact with each other is so different from the way that people interact with each other in my fields in physics and in academia. In particular, I will say, generally, the people that she works with have a much higher emotional intelligence or would score much more highly on an emotional intelligence score than a lot of the people that I work with. And that's not to malign the people that I work with or anything.
Well, there's theories about a lot of people in STEM may be on the spectrum.
Almost,
right?
Almost certainly. But the question then is which skills and qualities have you had to develop to be successful in a certain field based on the existing culture of that field? And I would argue that in a field like physics, and there's plenty of stories of people being, just wildly direct with each other, right? I would argue that they haven't had to develop, up until this point in history, actually, they haven't had to develop those emotional skills as well as perhaps people who worked in some other fields. That's just my argument. That's my hypothesis. So we can put that to the test later. But it's been interestingly borne out in the experience of the workplaces between my sister and I. But what's interesting, and in the book I cover, and I'm sure we'll get to it, but I cover this long sweep of history in particle physics. And as everybody sort of is aware now, a lot of these big experiments involve, multiple countries, hundreds if not thousands of people on these big collaborations. Now, I find that interesting because then you absolutely need the people skills, right? You need the emotional skills. You need not just structure, but you actually need, those what we would call a softer skill usually, right? So I find that an intriguing point in history where we're at, where actually I think to be a good physicist nowadays, you actually need all those sets of skills. And yet our systems and the culture of the field selects out for one side of that over the other side of that.
Interesting. Are you referring to some of these papers where the list of authors is longer than the paper itself?
Oh, yeah.
Which is really funny.
Yeah, I mean, they have systems, right, of how to do that authorship and how to do the internal review and then the external review and blah, blah, blah. But
he, et al. But the et al. Is... By the way, do you have an opinion on the Nobel Prize? The argument that it doesn't really apply now to these big, in physics, I mean, where you have so many authors. We're long past the lone genius working in the lab, and 1 or 2 or maybe 3 people at most can win the prize. That just maybe isn't appropriate now.
Yeah, I kind of agree with that. That it seems a little outdated now, given the way that a lot of science is done. And even in the book, I tell these stories of some women in particular who were overlooked for it based on sort of relatively biased reports, and so it's good to celebrate high achievers, and it's good to celebrate our successes as people and the breakthroughs that we make. But to celebrate particular individuals, especially when there's obviously 4 or 5 people who should get it, and it's limited to 3, which is just arbitrary, right?
Right.
And it's such an easy thing to change.
I know, just give it another name. It's like, well, Rosalind Franklin is the most famous example, I guess, in the last half century or so. But there was that guy, when they gave the Nobel Prize for the MRI, I forget his name, Daladian or something like that, a physicist. But he played a major role in development of the MRI. And he was furious that he wasn't included. They just listed 3. He should have been the 4th or whatever.
Yeah.
I mean, this poor guy was taking out full page ads in the New York Times. Well, I don't know what these cost, like $50,000 a shot.
Wow.
Yeah. yeah, saying, hey, you've left me out. Here's what I did, and documenting all his research and experiments, and that obviously played a role in this. It's just give him the prize. I mean, come on, make it 4.
Yeah, it's interesting, isn't it? Like I think, I mean, there is obviously like a detailed process, although it's quite non-transparent even to someone, in physics. I think I've met one person who I found out was on the committee or was able to like nominate people. But it's, yeah, I think it's right to question whether or not these structures, which have only existed, like the physics one, I think the first one was Wilhelm Röntgen, who opens my book, which I think it was 1905 that he was awarded the first one. I might have got the year wrong. And you sort of think, okay, well, a lot has changed in that 120 years, and the way we do science has changed. So, for example, the Breakthrough Prize, which is an alternative sort of fundamental science prize, awards to teams, which makes total sense to me. Like, the other thing with the Nobel, which is interesting from my perspective as an experimental physicist, is that experimentalists now especially have to work in these large teams, whereas theorists might still work in a more solo or small way. And a lot of the prizes are awarded for the theoretical breakthroughs while not recognizing so much anymore the experimental breakthroughs. And you sort of think, we all rely on each other. And when you talk to people in the field, there isn't so much of an animosity or it's just this weird thing that exists, which is this dichotomy between experiment and theory, and the fact that, okay, yes, if you're a theorist, you might have more chance of winning a Nobel Prize. And people joke to me occasionally, they're like, oh, Susie, you're still waiting for a Nobel Prize. And I was like, I think I'm more likely to get it in peace or literature before physics, honestly.
Right. By the way, Richard Dawkins always makes the point that no scientist has ever won the Nobel Prize in literature. And
interesting.
Yeah.
Was he taking that as a challenge?
Well, I think maybe, because if anybody deserves it, he's one of the handful of scientists that writes at such a high level, literary style, that deserves that kind of recognition, I think. Oh, I forgot to give credit to Brian Keating wrote that book on the Nobel Prize and the limitations of it now, and he makes a pretty good case that his research on whatever he was doing, I forget what it is now, certainly should be in the running. Anyway, it's just. Okay, last point on this. Simon Baron-Cohen, I'll credit him for this idea that autism and the autism spectrum and the larger idea we call now cognitive diversity may also play a role in the kinds of professions you choose to do. And that kind of thinking, Temple Grandin, the most famous example of this, she's just able to think in a way that the rest of us are not. And that actually leads to creativity and ingenious discoveries and so on. And so Simon Baron-Cohen, his book about this is kind of tracking, others have written about this too. So some of the geniuses in the past may have been themselves autistic or on the spectrum or whatever, something like that. So it's not interest or social or whatever, but it's this kind of cognitive style, the way you think about the world leads you to solve problems better than other people can, something like that. Anyway, okay, let's shift to talking about your book. It's very deep on experiments. So before we get into the specific experiments, I just want to talk a little bit of philosophy of science. So you have kind of Popperian, Karl Popper's falsification criteria, distinguishing between science and pseudoscience, that, we don't prove experiments. We just falsify all the ones, and whatever's left standing, we're reasonably confident may be true with a small t, something like that. But there's another way to think about it, more of a Bayesian analysis. That is, all those experiments you talk about in your book, they're kind of piling up, kind of shifting our priors more and more toward a higher credence in X, whatever the X is. And that you're not really trying to falsify anything. You're actually trying to test whether there's really some validity to the hypothesis. And the more evidence you can accumulate, then the better it is for you and your social group, fellow experts in that particular field. What are your thoughts on that?
Oh, great. Yeah, that's really interesting. I feel like in writing the book, it became really clear that there are very different motivations out there for choosing to do experiments. And so, for example, some of the ones I write about, some of the early ones were things where something was discovered accidentally, right? Someone literally, like Wilhelm Röntgen, 1896, he observes a glowing screen across the side of his lab where he's working with a cathode ray tube, a little glass tube with electrodes on it. And he sees the glowing screen across his lab, and he decides to investigate it, and he discovers X-rays, and those completely transformed our world, right? So that almost doesn't fit either of your theories, to be honest. It's like, how do you take serendipity into account? And then, at the other end of things, we have things like the Tevatron and the Large Hadron Collider. And by the time those big experiments and collider experiments were built, there were at least some fairly front-running theoretical concepts as to how particle physics worked on a very fundamental scale, and some predictions that came out of those theories, which predicted, for example, heavier quarks, with fundamental constituents in, say, protons and neutrons. And so then you're right, there is this huge drive to try and find, and this is something that has come into criticism lately from various aspects as well, as this sort of particle hunting way of doing physics and particle physics. I think there is space for both of those ideas, both the serendipitous, but also the sort of very driven. Okay, well, here we have a very compelling theoretical reason why this particular thing should exist, and if we can find it, then that makes, that means that the evidence we have for that theory becomes even stronger. And the standard model of particle physics is such a precise, like it predicts things to a precision of like 1 part in a billion. And then you can go out and find them in like a multi-billion-dollar experiment, and it's correct, right? The annoying thing about the standard model of particle physics, it's quite a complex theory now, right? It's been built up over decades and decades. The annoying thing about it, though, is that we can't find much that breaks it, right? So even at the Large Hadron Collider, there were hints, or there have been hints, that there are things which break this theory, and yet, now that they've gathered more data, they're like, maybe it's not, maybe it's still consistent. And yet, despite that, we know that this standard model of particle physics doesn't describe everything out there in the universe. So, for example, there's evidence from astronomy and things like that there's this dark matter and so-called dark energy as well. And there's all these things beyond our current level of knowledge. And yet, the ways in which we can make this theory, extend this theory out to what they call beyond the standard model physics, and then make predictions with that, and then search for those things in the colliders, and then come up with nothing again and again and again. It's an interesting and frustrating period, and it, at the same time, it would be astonishing to me if someone managed to find evidence that the standard model of particle physics was fundamentally wrong. So it may be that, for example, it eventually gets subsumed in a larger theory, as in, if you think about Einstein's theories of gravity, if you reduce them down to our everyday experience, you get Newtonian gravity effectively, right? So there may be a larger theory, and that our current one is just sort of an effective theory that works really well for what we can explore in our experiments at the moment. But I think the standard of evidence that we have for that theory is so strong now that it's very compelling. So then you have to sit back and go, well, how do we make the choices as a society about what it is that we actually research? Do we want to go on with another big collider program to find these other things, even though we know there are compelling reasons to think that there is physics beyond the standard model? We kind of know that that's true already. The question of whether or not a collider is the right way to find it is an interesting and open question. And there are other, smaller competing experiments that may find something first. Or it may be a more serendipitous approach. One thing that a lot of people have pointed out when they read my book is, in the early phases, we get this serendipitous idea of discovery because the equipment that you need can be small, lab-based, you might be able to visually see an effect with your own eyes, and discover something that way. And that nowadays modern science it comes across as sort of less fun because that probability of having that serendipitous discovery seems to have disappeared, especially in something like particle physics. Personally, I think that's a bit of it's a dampener. Like, um, but where I try and take people with that is, okay, well, that may be true if your aim is to discover a new particle. Yes, it's now harder to discover new particles. That I cannot disagree with. Like, we just need these way bigger experiments. It's, you know, very, very rare processes, so you need lots of data analysis, big computing systems, etc. There's no way around that in that field. But the serendipitous things that come about now are things like, oh, well, we invented this new detector for particle physics. And look what else this could do in the world. To me anyway, it seems like
You mean applications?
the applications, and then also just the potential that this stuff creates in other fields is really of interest to me. And I mean, I ended up working at the moment in how we use particle accelerators, little ones, way smaller than the Large Hadron Collider, for cancer treatment, and the potentialities that we have to be able to translate these technologies to different fields is really exciting. It's not quite the same as a serendipitous discovery, but when I walk in a room full of people who are used to the existing technology and I'm like, oh, our new technology that's coming out of the lab could do this and this and this, they're like, what? To them, it's as if I've found X-rays across the room, right? It changes their view of what is possible in something like oncology. And that's, so I feel like now we're at this point where those intersections between fields is where the serendipity is going to happen. And also, to come back to what we were discussing earlier about the people skills and the emotional intelligence, being able to communicate across those boundaries with people who perhaps don't have a physics background, and being able to pull together a collaboration to build on something new when you all have different and diverse backgrounds and different and diverse ways of thinking, including potentially neurodivergent folks within that community. I think that's where the exciting stuff is happening.
Yeah, it's like, I think of science as a three-legged stool where you have data, theory, and communication. You got to be able to communicate. And I don't mean just pop science writing. I mean communicate to anybody about what you're doing. Your book does that very well. A couple things. So as I forget, it was Asimov or Arthur C. Clarke who said science progresses not by eureka, I found it, but that's weird. So your point is that it would be harder to, in one of these massive particle accelerated experiments, for that to happen, for everybody sitting there, all 10,000 people working on it, to go, that is a completely new physics that we didn't know was there. You're saying that's not likely to happen.
Well, I think so. That could still happen. And that's kind of what people are hoping for, is that something might crop up in the data that they weren't expecting. In fact, that's, in a way, it's hard to put it this way, but that's what you expect to happen, is that something unexpected crops up. Partly because that's what the history has told us. A lot of the things that were discovered in particle physics, like the extra generations of, so if we have the electron, there's extra generations of the electron called the muon and the tau, sort of heavier versions, which are short-lived particles. No one predicted that those existed at that time, right? When they were discovered. Antimatter was discovered without the person who discovered it knowing that it had been predicted 3 years earlier, or a number of years earlier.
Wow.
He just found evidence in his experiment of something going, kind of bending the wrong way. It's like, it looks like an electron, but it's bending the wrong way in a magnetic field. And he, experimented on it and eventually came to the conclusion that it must be like a positive electron or a positron. And then even later on, there was this period in post-World War II, especially in the US, with these big accelerators called the Cosmotron and the Bevatron, and later the what was it called? The AGS, the alternating gradient synchrotron. And they just kept finding more and more new heavier particles. And they didn't expect that complexity. And so I think the reason I retain hope for these large experiments in the future plays into that, which is if you create a new possibility of reaching territory that nobody's reached before in terms of energy reach in a collider, in terms of how many collisions you can get in terms of data rate, I think there's a strong likelihood that something is going to show up that you didn't expect. Now, if you talk to a theorist, they all have different ideas about where that's going to show up, and there's very little indication in some of those theories as to whether that is just a bit of a step up from the Large Hadron Collider, or like we'd have to build something the scale of the universe to do it. Like, unclear. It is unclear how, okay, not universe, maybe solar system. We're not going to do that, FYI. But so it's unclear where those new discoveries are going to be made, and yet there's compelling reasons to think that they will be made.
Now, would dark energy and dark matter be in that category of this is we don't know what it is, and this is a discovery to be made?
Yeah, and as an accelerator physicist, I work on the machines, so I'm sure there's many fascinating theoretical physicists out there. You could drill in on the different theories on this one, but as we understand it at the moment, the matter and all the stuff that we've discovered, over 120 years of amazing invention and discovery that's in my book, only covers about 4 or 5% of the mass energy content of the universe as we know it, right? It's like everything.
That's such an astonishing idea,
isn't it? And then within that, the stuff that makes up our everyday existence is like 3 particles and some light. That's about it. And so this astonishing complexity of like just what is out there in our universe and how it's built on a fundamental scale, and how little of that we get to interact with as humans in our day-to-day lives. And yet how incredible it is that over the space of just like 100 years, we've managed to invent technologies and build technologies that are able to measure these things to the point where we can say about our universe that there is this complexity out there, that we know it must be there. Here's the evidence for it. And that we can even go on this wild adventure to just follow our curiosity to be like, yeah, how does our universe really work? And so the fact that, of all the matter that we know of is only 4% of what we think is out there. And that's the challenge for the next generation, as far as next generations, plural, as far as I'm concerned, is to figure out, I think first of those is dark matter, which we know interacts gravitationally, but that appears to be the only way that it interacts, that there's evidence from rotation curves of galaxies and things like that that show that there is more mass out there than we would expect. And so there's lots of experiments happening at the moment and lots of theories to try and figure out what dark matter is. Some of those rely on the big colliders. So the evidence of dark matter might come through, so you would have heard of the Higgs boson, which was discovered in 2012. So how dark matter shows up in our universe can influence the specific properties of Higgs bosons in those experiments, for example, or the interactions of Higgs bosons. And so there are people who are, using Higgs bosons that we only discovered in 2012 to try and make that next leap to understanding what dark matter might be. And that is just, this inexorable building of knowledge again and again and again, to sort of say, okay, now we know this thing we think exists, pretty sure. If that thing exists, then what about this other thing? Let's go and look for that. And even I didn't expect to see all of this happening within my career. When I first learned about these concepts, it's like we have this bias where we think, oh, well, that might happen eventually, but not in my lifetime. The Higgs boson was one that I thought might not be discovered in my career, and it was discovered fairly early in my career. Gravitational waves was another one. I was a big doubter of the gravitational wave. I will admit that, because I think it's important. Wow. I think it's important in our funding schemes, in the way that people support science. I think it's important for even me as a trained physicist to be able to say, I doubted that and I was wrong. Yeah. Why? Because I didn't understand. Yeah, I didn't understand what they were going for. I didn't understand where the predictions lay of exactly what precision they needed in their gravitational wave detector to be able to actually see what they were looking for. And they improved it and they improved it and they improved it. And eventually they got there, and suddenly a whole new type of astronomy, of gravitational wave astronomy, opened up to discover our universe.
Yeah, I had Kip Thorne on the show. He's a longtime friend and supporter of skeptics at Caltech when we were at Caltech. Yeah, it's just the measurement is just astonishing. Like, how in the world do you control for like a truck driving by a mile away could erase all your data?
Even I think it's like cattle as well. Like animals walking can even affect their data.
Right. It's just amazing. Okay, so as I understand it, galaxies of a certain size and so forth, you'd predict that it should be rotating this particular way. The mass we can see, the rotating galaxy would just kind of come apart. but it's being held together. So there's obviously something more than the stars and gas and particles we can see. And so when people like you say, well, it's dark matter, you don't mean that as an explanation, a causal explanation.
No,
this is
no.
like a linguistic placeholder. We're just
Yeah.
going to call it that because we have to talk. Now we got to go find what it is.
Yeah, I should say people like my particle physics colleagues. As you
Okay.
said at the start, I'm an accelerator physicist. Although my undergraduate projects and things were in particle physics, so I have a little bit of experience there. But I shouldn't lay claim to being the physicist who is looking for that, right? But yeah, I guess we do. It's helpful to give these things a label, and there is many different theories of what dark matter might actually be. And so yeah, I think we just say like that's this is a type of matter. It interacts gravitationally. We know very little else about it at this point in time.
And then dark energy would you need to explain why the universe is expanding at an accelerating rate. Is that right?
That's right.
And that was a surprise discovery in the late 90s, I think that was.
Yeah, that this sort of factor needed to be in there in order to explain the evidence that we have about the expansion rate of the galaxy. And beyond that, you'd have to get one of your theoretical folks back on the show to sort of dig into exactly what dark energy might be and the competing theories on that front. Yeah.
Yeah. Okay, so let's go through some of these classic experiments. You can riff on any of these that you like. You start with the cathode ray tube and X-rays and the electron, the gold foil experiment, the photoelectric effect, maybe, and cloud chambers. I always thought that was such a weird label, a cloud chamber. It's something meteorologists use right now.
Well, so that's an interesting convergence with the story, actually, because the person who invented it, CTR or Charles Wilson, who was working in Cambridge in the UK at the time, and he was working alongside all the people doing the fundamental work in radiation. But his first love was meteorology.
Right.
And so he went to Ben Nevis in Scotland, he was from Scotland originally. And Ben Nevis is the tallest mountain in Scotland, although it's not very high. But it's always cloudy up there, right? And so he went there one summer to do a sort of meteorological expedition, and he goes up there, and the weather is beautiful, and he's watching these particular effects of light on the clouds. So they have things called glories and the Brocken spectre, and these sort of things where light makes crazy halos and shadows and interesting visual effects. And he thought, that's really fascinating. I'm going to go back to the lab and I'm going to build a device which can recreate these effects in the lab so that I can understand how these optical effects are working. And so he goes back to the lab and he builds out of glass. So he was quite a skilled glass blower. He builds out of glass this device which sort of pumps and opens and closes and has pistons and things and lets water expand so that it goes into what's called a supersaturated state. So it really, really wants to form cloud droplets, but it can't without something for that droplet to form on, which we call a nucleation site. And so they understood already at that point that that's how clouds were forming, so he knew that's sort of how he had to do it. And to test it, he kept pumping it open, and he knew that if he had regular air in there, and regular air has some sort of dust and dirt and whatever in there, he sort of thought, okay, well, with regular air, it should form a cloud. But what I'll do is I'll send through clean air again and again. And with the clean air, with no dust in it, really did a really good purification job, then it shouldn't form clouds anymore. And he found that it sort of seemed to anyway. And that was really confusing. It was like, maybe I'm just not purifying the air properly. And he sort of set it aside for a while. And then in the meantime, people discovered things like X-rays and various forms of radiation. And eventually he sort of had this idea, maybe it's the electricity of particles in the air that's causing these little cloud droplets to form. And so eventually he went away and he redesigned the whole apparatus, and he redesigned it so that he could intentionally see things like radiation, because as radiation travels through the air, it will ionize, so it will rip the electrons off and form ions. And he thought, if that's true, maybe I can visualize this radiation that's being formed. And the first time he tested it, he took an X-ray tube, which, had only been working for a few years because we'd only discovered X-rays a few years earlier. And he put it up against his cloud chamber, and he saw like a spray of X-rays. And so suddenly these invisible X-rays, which everybody had been wowed by because they could see through the human body and were already being used in hospitals. And suddenly he's able to see the effect of those ionizing the air inside his cloud chamber. And it completely transformed the way that people studied and viewed radiation. Because until that point, and even now, one of the weird, scary, interesting things about radiation is that we can't see or experience it with our own eyes or bodies. And until that point, they'd been using devices called electrometers, which are like basically a tin can which counts charge. But it's a very difficult, it was easy to make, but very difficult to use well as an apparatus. And suddenly he had this chamber type in which, as it expanded, you could actually just see the interaction of particles in the air as it went through. And so people started using these chambers, taking them all over the world, up mountains. One was even sent up in a fighter jet at one point. And they were used to make a whole lot of early discoveries. So one of the biggest early discoveries with it was in 1932 when Carl Anderson went up a mountain with it, and it was a real struggle to get it up there. And he'd built it in. There was a recession at the time, the Great Depression, and he had scavenged together all these different parts for it. So he had these big copper coils around it, and it was powered by a motor generator that consumed most of the electricity of the Caltech campus. So he had to run it at nighttime because otherwise the rest of the Caltech campus would complain, and it would make these banging noises when he was testing it there. And eventually they put it on a truck and they take it up a mountain. And that's when he starts seeing these tracks in his chamber that are the ones that turn they look like electrons, but they're turning the wrong way inside the magnetic field. And so then he does a few more detailed experiments and comes out with this idea that these are positive electrons. And it was the very first evidence of antimatter. So like matter, but the opposite form. And no one predicted it that he knew of. But actually Dirac had done the theory in 1929, which predicted antimatter. But even he didn't think it was real in nature. Until this evidence came about. So suddenly you've got this visual method where, like before, you would have had to line up a series of detectors in order to figure out the direction in which things were moving. But there would have been no way to tell that a particle had passed through your detector one at a time. So it created this completely new way of seeing the fundamental realm. And so, positrons were found that way. Muons were found that way, so the heavy version of the electron, by Carl Anderson's student as well. And a whole lot of discoveries. And they were even later used, they would be triggered to expand at the right time during collisions from particle accelerators later on. And for a couple of decades at least, these detectors were really the mainstay of discovery in particle physics. And I just still think they're one of the most beautiful and elegant pieces of equipment. I mean, you can literally build one at home now, not the expanding ones, but one with a sort of alcohol vapor that falls down. And they are just mesmerizing because now I can build you one of these in half an hour, and you can turn the lights off and shine a torch on it, and you're seeing cosmic ray muons from the outer universe, and you're seeing alpha particles from the decay of radioactive substances in the materials around you. And you can just sit there and just watch the effect of these particles.
That's amazing.
Go through, even though, for the entire history of humanity, we had no idea they were there until that device was invented.
Amazing.
Mad, isn't it?
Can you order it on Amazon?
Maybe a kit.
See? That's the next point.
I'll have to make a kit, won't I? That's
it. Yeah. No, instead of a chemistry kit or one of these little robot kits for parents to buy their kids, something like a cloud chamber could be interesting. All right, so let me see if I understand this. The thing that's coming through the cloud from these cosmic rays, they're particles, or are they energy? What? How would you describe it? And where do they come from? What produces them?
Yeah, so as we understand it, cosmic rays were discovered in about 1911. That's earlier in the story as well by Victor Hess, who went up in hot air balloons and for the first time discovered there was more radiation as he went up in the atmosphere than there was down on the ground, which sort of led to this understanding and challenge to try and understand what this radiation was that seemed to be coming from space. He very cleverly even thought, I wonder if it's coming from the sun. And so he did a balloon flight during a solar eclipse and managed to establish, he managed to establish using that it wasn't, it didn't seem to be the sun, that they did also seem to be coming from the rest of space as well. Like there wasn't a big difference, basically. And so as we understand it now, and there's still some mysteries out there in terms of what cosmic rays are, and astronomers love to study the sort of high energy and wild cosmic rays, but most of them are high energy protons coming from space. And some of them have energies that are like trillions of times higher than the Large Hadron Collider beam energies. And it has been a real challenge to understand exactly the mechanisms of how those very high energy protons are formed out in space, in sort of cosmic particle accelerators, as it were. And I guess when you get large tracts of time and space and magnetic fields, which we now know are out there in the universe, then you sort of start to think, okay, well, between gravity and magnetic fields, there's probably some mechanisms whereby these particles get sort of spun up, whether that's out of a black hole or a quasar, or, spun up and spun round and sort of somehow accelerated to these enormous energies. But personally, I would really like to understand exactly how that process works in case we can learn something about that for how to build our experiments better on the Earth, or how we could
you
use
mean
them.
like a quasar maybe as a source of cosmic rays? So you would
they seem
build
to come
a
from all
small
sorts of
version
places.
so if you could build a small version of that and a little bit of cosmic rays came out, that would be an experimental test of it.
Something like that. I mean, that would be a very hard challenge, but
Yeah.
in terms of the density of the object. But if we could understand just the mechanism by which they're accelerated, I think that could be really interesting. And there's people trying to understand that from different walks of life. So often these high energy particles start as protons, or sometimes there's sort of gamma rays as well, which there's gamma ray astronomy now that where we measure these things. So basically just high energy particles or high energy photons, and the protons, which is most of them, will come in and interact with our atmosphere, and then as if our atmosphere was like a target in a particle accelerator, those protons are going to smash into all the gases and dust and everything in our atmosphere and create secondary types of particles. So then you get this ability to create things like muons and other more exotic particles which don't live for very long. So a muon only has a few microseconds of lifetime. But because it's just created in our atmosphere and comes down to the Earth, it lasts long enough for us to detect it down on Earth. And so this is why all the early experiments in particle physics were done using cosmic rays, because you've got this source of them from these protons hitting our atmosphere and generating new particles. In around the 1940s, the ability to make new discoveries that way kind of came to an end, though, because it's very difficult to take this very disparate shower of particles coming from space through our atmosphere and actually use it to get enough data to make detailed discoveries. So that's why in the 1940s, when the particle accelerators were invented and got large enough, they sort of became more prominent as the tool of choice, because suddenly you could then organize exactly which type of particle, you could focus it into a little beam, you could have, many of them in a tight area, and you could have that sort of controlled laboratory environment. But it's interesting that now when we're thinking about these larger scale, big picture questions like dark matter, a lot of the detectors again become more passive. They're sitting there and they're waiting for things traveling to us from space or through us, as it were, and trying to gather enough data by being a very large volume of detecting material. So there's still even now the place for using cosmic rays or sort of cosmic radiation to make major discoveries. And this early discovery of cosmic rays and all the things that came from it was really that first thing. And there's still things still things being discovered all the time that way. So, neutrinos, for example, are coming both from the sun, but also from there's also geoneutrinos from the Earth, and then there's neutrinos from space as well, and from cosmic rays. And those have been used to really help us understand that even with neutrinos, which are like these little ghostly particles which are emitted in beta radiation, I mean, they hold some of the mysteries that are really pointing the way forward in particle physics today, because we don't understand their properties fully. Yeah.
Remember, one of the arguments of what we call the no moonies, the people said we never went to the moon, was that you can't leave the Van Allen belt because these cosmic rays will destroy bodies. But apparently that is, and you could do it for 3 or 4 days or a week or so. But maybe going to Mars, where you take 6 months to get there and a year to get back or whatever it is, that is too long a time, because these cosmic rays do go through our bodies. Perhaps they could cause cancer. This is the argument I've heard. But you could shield the spacecraft in something, lead, water, I don't know what, that would then pick up most of those cosmic rays and disperse them before they get to the human bodies.
Yeah. I mean, lead, water, or even a sort of magnetic shielding to bend particles around, right, as well. And one of the, I guess some of the interesting studies that I know people working in, including the acceleration mechanisms of these charged particles, is also like, if you could understand that, maybe you can reverse it and then get rid of these high energy particles if you were to travel in space. But yeah, the understanding of the impact of radiation in space on our bodies is a really important subject, and it's really difficult to study that, especially because of the way that we quite rightly control radiation exposure in our society now that we understand that it can have incredibly damaging effects as well as positive effects. If you direct it correctly, you can kill cells to treat cancer. If you direct it incorrectly, you can kill cells and kill people. So, double-edged sword. So we control it very, very tightly. But nowadays we do some of those studies on space radiation effects and biology at labs that also treat patients, or labs that are doing research in particle physics. So big labs like CERN, like Fermilab, Triumph in Canada, they often have parts of the laboratory dedicated to the understanding of the impacts of space radiation on biology. So it's a very active field at the moment.
Interesting. Okay, I got a question for you here. All right, what is that? Light.
What is that, light?
Sure. Yeah. What is light? What is light? Where is it coming from?
Okay.
I mean, so it's coming from inside the atoms that make up. I don't even know how my iPhone light works, but let's say I have an incandescent light bulb and it's heating up, and the particles of light are coming out. What are they coming from?
What are they coming from?
Where were they? Where were they before I turned the light on?
Well, you can. Yeah. So you can. So I mean, photons as a concept are quite interesting, right? Because and I cover this story in the book as well, as this early idea of photons and light and energy and what exactly light is made of, and this sort of wave particle duality idea. And it actually started with the idea of an incandescent light bulb and the color of something like an incandescent light bulb, or as a physicist would call it, a black body radiator. So something that is like a perfect radiator of radiation. And they were sort of trying to understand the shape of the spectrum of the color of light that comes out at different temperatures. And by studying that in detail, they were able to sort of go, okay, something's not adding up here. Like, our idea of how energy works and generate, like the idea of generating light from that isn't quite adding up. And so it was Max Planck early in the 20th century who managed to solve that problem and get the sort of mathematical curve to come out correctly by putting in a trick that said that light comes in chunks, some minimal chunk size, which he called a quanta. And this, he did not believe that energy came or light came in chunks. In a realistic physical sense, he thought it was just a mathematical trick that he put in to make the equations work. And then a few years later, Albert Einstein takes that one step further, and he uses this idea of light quanta to describe an experiment called the photoelectric effect, which is where you, sort of the opposite of what your phone's doing, where you shine light onto a metal surface, and then electrons jump out. So the energy is transferred from the light, excites something in the object, and then electrons jump out, which causes an electrical current to flow. And by using this same concept, Einstein managed to come up with an idea that said, okay, but the intensity of the light doesn't matter. He says, these chunks of light have some minimum energy. And if you don't have sufficient energy in the chunk of light, you won't liberate any electrons from the metal whatsoever. So he sort of motivated, in a way, the idea of doing experiments to check with the frequency of the light how many electrons, or the current that flowed from it, not just the intensity. And until that point, people had thought it was dependent on temperature. They thought it was dependent on the intensity of the light, and it was really that idea that led to this concept that, okay, no, it's the frequency of the light that matters, because if you have a specific color of light, that color corresponds to a certain energy, and below some cutoff energy, no electrons are going to jump out. And so over in the US at Caltech, Robert Millikan had been studying this effect for quite some time with very little success. And he ended up experimenting on this for 12 years, not because he was trying to prove Einstein right, and this comes back to our philosophy of science again, but because he was trying to prove Einstein wrong. Because at that point in time, people believed so strongly that light was a wave. Because this wave particle thing of like, what is light, had been going on for centuries, actually. And they'd come to really strong conclusions with a lot of evidence that light acted as a wave. Because if you think about things like reflection and refraction and diffraction of light, all of those things had been measured. And even the way that light interferes, right, and can make these nice interference pattern fringes, all of that had been studied. And so very successful wave theory of light. Why would you overturn that, right? So Millikan says that Einstein's hypothesis is a reckless hypothesis, and that surely there's some other way to explain this photoelectric effect that doesn't involve making light a particle, which is effectively what Einstein's theory, or this quanta or chunk theory, predicted, was that light came in as a particle. And he spends 12 years in the lab with multiple graduate students over years and years, perfecting his apparatus. And in the end, every piece of data that he has proves that Einstein and Planck's theory I wouldn't say proves that it's correct, but it all agrees with Einstein and Planck's theory. And in fact, he makes the most accurate measure of Planck's constant, which is the gradient of this graph of the energy of electrons out versus the frequency of the light in. He makes the most accurate measurement of Planck's constant that anybody has ever made up until that point. And the psychology of the researcher, right? He really struggles with it. He's really he thinks he's failing because he's not measuring what he, in his biased hypothesis, thinks that Einstein cannot be right. And yet a number of years later, after his experiments, at least a decade went by, and he was eventually awarded the Nobel Prize for that and for his other experiment, which is his more famous one, which was measuring the charge on an oil drop, so measuring the fundamental electric charge. And he was awarded the Nobel Prize for that in, I think, 1929. And by the time he gives his Nobel Prize acceptance speech or his lecture, if you read it, it's very much like, when I set out to measure Planck's constant, or to measure Einstein's theory of the photoelectric effect, and he's completely changed his tune, like now that everybody else has sort of come to accept quantum mechanics might actually be real, he's sort of come to realize the importance, and again, the Nobel Committee have come to realize the importance of his measurement in underpinning that understanding. And yet he didn't set out to prove that at all, actually, when you really look at it. So I find that whole thing really fascinating.
There are criticisms of scientific papers because they're structured in a way that, here's the background, here's what I set out to test, here's the experiment I did, and here's my conclusion, as if that's what they actually did. And it's almost never quite that structured.
Yeah, it's really interesting as an advisor to graduate students to have that discussion around paper structure and the story. And it's like, okay, we're telling a story, but that, at first, they always want to write the story exactly how it happened, right? And it's like, okay, well, that's not really going to work as a story because,
Right.
if 3/4 of the way and you realize that you were just doing something wrong the whole time, you can't really like,
Right. Right.
although, like it would help science along if we were honest like that, right? If we just were like, oh yeah, I got 3/4 of the way through and then realized that this thing is really important. But usually I encourage people to write papers in a way that highlights the importance of that thing, but but doesn't bore people with 3/4 of a paper that becomes irrelevant at some point.
Well,
But it's interesting, that recording of science. Yeah.
on the question of what is light, is
Mm,
the answer it depends on what experiment you're running?
pretty
Sometimes it's a
much.
particle, sometimes it's a wave.
Yeah, yeah. I think also the way I think about it anyway in my own head, and someone can disagree with me, but I think about it in terms of that we are biased because our everyday experience and thinking of things like, when I say particle, even I still think of a little billiard ball.
Yeah.
Totally
Yeah.
wrong, right? It's
Right.
like a probability wave. Um, but somehow our the first concept that we learn of something, like that first time you ever saw a picture of an atom and the particles in it were little billiard balls, really
Yeah.
hard to shake. Really
Yeah.
hard to shake. And likewise, our ideas of light. Often our first experiences with light might be based on our everyday experience, and certainly based on understanding it as a wave. And if we even when you think about when you've learnt about waves or different waves you've experienced, like at the beach, or sound waves and pressure waves, you sort of have this working model intuitively of what a wave is like or what a particle is like. And I think we bias ourselves in what something like light is, which is fundamentally it is just light, right? It behaves how it behaves. And the fact that we have these mental and mathematical models that describe it as a wave or that describe it as a particle is kind of our fault, right? So that's the way I think about light, is like it is this entity, and we've created these models and these ways of understanding to match things within our intuition, which we already understand. But there's like
Right.
it's like that's the mystery at the heart of it, is that
So maybe the
realistically,
maybe it's maybe instead of saying it's like this or it's like that, it's not like anything. It's its own thing. Like
yeah,
a black hole is not like something else. It
right.
just is what it is.
Yeah, but you can visualize it in different ways, and you can write down mathematics that describes it, and you can test that mathematics, works with experiments, and you can make predictions. And I mean, that is the wonder of the physical sciences, really, is that predictability. But when it comes down to the philosophical, like, but what is it really?
Yeah, right.
Sometimes it trips us up, I think.
Right.
Yeah.
But I guess what I was asking, where does the light come from? Where was it before I flipped the switch on? And maybe the answer is it wasn't anywhere. It's being produced by the action inside the atoms or something like that.
Yeah, yeah. I mean, I would think about it more in an energy transformation, right? So if you take an atom, and an electron in one of the orbitals jumps from a higher orbital to a lower orbital, there's an overall energy difference in the state of that atom. And what's produced from that, the sort of energy that's emitted, which is emitted in the form of photons or light, exactly matches that energy difference, so that overall energy is conserved in that
Mm.
interaction.
And is that what radiation is also?
Yeah, the light-based forms of radiation, yes, but also the particle-based forms of radiation. So if you emit an alpha particle, for example, or an electron or beta particle, yes, same thing. If you just add up, using conservation of momentum or conservation of energy, you will find that you can sort of literally just add all these things up together, and all the pieces fit back together, because that's, when you understand the fundamental interactions, you can just add them up like that. And that's really fundamental to our understanding also of the interactions in these big particle colliders. If energy or momentum wasn't conserved, we'd have no idea what was going on. It's a very powerful tool.
Mm. Interesting. Okay, so why does radiation happen? Let me think about it this way. Like potassium argon dating in
Mm,
geology of lava flows, say, and the reason it works is because it's predictable how much of the potassium atoms will decay into potassium argon
mhm.
atoms. But why does any one particle decay at all? I mean, and apparently it's random. And let me ask you that. Is it really random, or is it just we can't predict it?
So I wouldn't use the word random so much as probabilistic.
Oh, probabilistic. Okay.
Yeah. So yeah, within some quantity of, say, potassium, or some other, potassium 40 or some other radioactive isotope, what we do know is that there's a predictability to the half-life of that, right? So within some period of time, half of the atoms will have decayed. As to exactly which one, like, if I choose atom 372 and I
Right.
say and I say, when will that specific one decay? I cannot tell you.
You can't,
That
right.
might seem random to atom number, to particle number 372. But overall, if I take thousands of them at the same time, I can say that, if I take 1,000, then after n minutes, 500 of them will be left. But that's what we mean, I guess, by these more probabilistic or stochastic processes, is that we can't necessarily predict in a deterministic way the individual trajectory of the individual particle, but we can predict overall what's going to happen to the collection. There's something quite fundamental in this idea of radioactive decay to me as well, which I'd like to bring in. Two things I'd like to mention. First of all is one of the women that I brought back into the story here is Harriet Brooks, and she was Ernest Rutherford's first graduate student in Montreal in the early 1900s. And I'd never heard of her before, which possibly to someone in North America might be a surprise. I don't know if you've heard of Harriet Brooks before.
Not until your book.
Right, yeah. So she was his first graduate student. I think technically she did her master's with him, but then she went on to do research and get her PhD. And she did some of the underpinning experiments, understanding decays of sort of thorium and radium and things like this. And her precursor experiments were really important to Rutherford and Frederick Soddy, who was the radiochemist that he worked with in Montreal, to understand this concept of half-life. Now, her story is, just as a brief tangent on the women in physics front, her story is quite interesting because she does this amazing research, and she's very respected by Rutherford, but very self-effacing in her communications with him. She's always putting herself down, basically. But she, at some point in her research, she was approached by a man that she knew and asked, he asked her to marry him. And so she got engaged. And she went to her college, which was an all-women's college at Montreal at the time, and she told them that she was engaged to be married, and realized that she would have to quit her job if she got married, that she would have to quit doing physics, teaching physics, and she couldn't afford to do it for free because her family didn't have enough money to support her and the 6 other children. And so she was very self-supported through scholarships, through her incredible intellect. And so she realized that if she married this guy, her career in physics was over. So she broke off her engagement, and she fought the college as well.
Wow.
So she fought the college and she broke off her engagement. And she went on to do more research. She went to the UK and worked with J.J. Thomson, who was Rutherford's graduate advisor. She eventually goes and works for a little while with Marie Curie. And Rutherford really tried to help keep her in research. But at some point she was in Europe. He'd moved to the UK, to Manchester, where he went later. And he was trying to get her to work with him there. And his reference letter for her described her as basically the Canadian Marie Curie, she's the most prominent woman in radiation research other than Marie Curie in the world. He thought really, really highly of her. And at this point, she's about 30, right? Which at this point in time in the early 1900s, is about 1920, I think, by this point. It's a pretty, for a woman to be 30 and unmarried with no kids is
an old maid.
Right. It's like, this is your last chance, And one of her old tutors from Canada started courting her and sending her letters. I think she was in London at the time. And so she has this really difficult choice to make, this sort of work-life choice, effectively. And despite Rutherford offering her, a pretty good job at Manchester with this amazing reference for this fellowship she was going to get, that societal pressure, I think at that point, was just so strong for her, and that, scarcity of needing to have financial stability because her family couldn't support her was just too much. And she nowhere has she written about actually loving this person. It seems to have really been, okay, I need to make a decision here. And she married him and she went back to Canada and she had 3 children, and her career in physics ended at that point, which I always think, like, first of all, that's why I don't know her, is because her career was cut short. And also, like, what might she have done alongside Rutherford if she'd been at Manchester? It could have been, but on the flip side, I do think it's important to recognize and write back into the story people, even if their careers didn't, end up in Nobel Prizes and Fellows of the Royal Society. So, so she's an amazing story. But the other thing I wanted to mention about radiation generally is how much of an effect it had on sort of people's psychology or philosophy or understanding of the world that we lived in. And the fact that the fact that the atom itself is mostly empty space just blew people's minds, including, famous artists and people like that. But also this idea that nothing in the world is stable and unchanging, right? Basically, everything in our entire universe changes. To me, that's a really fundamental philosophical concept. The only constant is change, right? This is the thing that people say a lot. But we often think, oh, yeah, that's true. But rocks, surely rocks are different. Oh, no, rocks are decaying. And the fact that then we can use these, such a fundamental physical principle as the idea that even the atoms within rocks are going to decay, and we can measure in the lab the probabilistic decay rate of that, and then we can use that to go out into the world and understand how old the Earth is itself. For example, Rutherford famously, when he was at Montreal, he had this rock in his pocket, and he walks up to the geology professor, who's called Frank Dawson Adams, and this is, he has to go at Adams. He says, Adams, and Rutherford was like this really boisterous New Zealander guy, right? Like tall, loud, and he goes, Adams, how old is the Earth? And Adams is, he prevaricates a little bit, and he's like, oh, I think it's about, based on best estimates, about 100,000 years old or something. He says something like that. And Rutherford pulls this rock out of his pocket, and he's like, I can prove beyond doubt that the Earth is at least, I think he said 700 million years old. And
right.
This rock is 700 million years old. It was a piece of pitchblende which contains uranium, and he invented the uranium-lead radiocarbon dating process, which was one of the first, radiometric dating process, which is one of the first radiometric dating processes. And so, I mean, he's a bit of a showman, right? And of course, then he had to go and prove to the physicists as well that this was true. And now one of the reasons that we know, for example, the age of the Earth itself, and the age of various ancient artifacts and things is by using these different methods, by measuring the fact that one atom decays into another atom over time, which just, it blows my mind how this connects up different fields like, ancient history and geology along with physics. And so it also like makes you just go like, why do we separate the sciences? Like, why is that?
Oh, we shouldn't. No. It's all balkanized. Yeah, forget all those buildings and brick walls and stuff like that.
Yeah.
Now I'm reminded of that geologist John McPhee's opening line in one of his books, which was about deep time, that the top of Mount Everest is marine limestone.
Oh, that's lovely.
Yeah. This was once under, was 29,000 feet up. How did this happen? Right. I mean, this is kind of in the retracking the era of Charles Lyell and, kind of post-Darwin evolution. Even rocks evolve, even volcanoes and islands, island geography, island geology is very active.
Yeah.
Right. So stones are not fixed, right? Okay,
and if you've ever been to Iceland, that is like the fact that geology changes is very present.
Yes. Yeah, you can't fly out today because there's too much volcanic particles.
Volcanic activity.
Yeah, exactly. Yeah. Okay, so back to let me just ask about this probabilistic idea. So if I flip a coin, it's 50-50 heads or tails. If I flip it 1,000 times, you're going to tell me, well, it's probably pretty close to 500, could be 510, 490, but it's going to be close, right? But if I flip a coin once, right, it's either heads or tails. Now, I don't know what it is. So when I say it's 50% heads, 50% tails, I'm just talking about my ignorance of the system. it's 100% one or the other, right?
Yep.
Now, but the Heisenberg uncertainty principle is saying something different. It's not just human ignorance of the system. It really is truly random built into it. Is that, am I saying that right?
Yeah. I mean, so again, again, I wouldn't use the word random quite.
Okay. All right. Yeah.
So I guess it's a true uncertainty built into the system.
Yeah.
Which is that we can only like, you know, in the Heisenberg uncertainty principle, it's sort of position and time or something like that, right? Like we can know exactly where something is, but not when, or we can know exactly, you know, the time of some process, but not exactly where it's taking place.
Mm-hmm.
And that, yes, there does appear to be this fundamental quantum mechanical limit to what we can understand, not limited by our actual technology, right?
Right.
And this sort of seems it seems hard to grasp, but when you work in a field like something like particle physics, the fact that something has this sort of more probabilistic nature is like part and parcel with the field. So, for example, the mass or the heaviness of some of the large particles determines their how long they might last before they decay, and so there's just a fundamental uncertainty. So when we make these measurements of even the mass of a particle, there's a width to that mass because of this inability. And even if we built the perfect experiment, there'd still be a width to that mass. There's still some sort of fundamental uncertainty in it. And I sort of, I always come back to how do you actually measure things, right? Because I'm an experimentalist. But again, like I'm sure there are many people who've written many things on the sort of philosophy of this idea that there are things in our world which are sort of fundamentally unknowable beyond some point, and that appears to be one of them.
Yeah, such that it might be a Mysterian mystery that we can't know. And it's not just, even if we had a brain the size of the Earth, you still couldn't know it because it's built into the system.
Right, and it's one thing to not be able to know it beyond some point, and then it's another thing, and I do always point this out as well, it's another thing to be like, but we can use it. Right? So we're already using it, certainly in particle physics experiments. But these underpinning quantum mechanical ideas, they're not just like things which we've written down and experimented with in labs and then gone, okay, yeah, that's how the universe works. You held up your phone before, right? Just about every device in there relies on quantum mechanics and came from some extent, fundamental scientific research and government-led research.
Is that your answer to the politician's question? Why should we spend $50 billion on this particle accelerator? What good is it?
That's a really good one. I want to read a response that was given by Robert Wilson, R.R. Wilson, who was the first director of Fermilab, to justify the building of that machine before they even had any idea what it would come to. And he was put up in front of the Senate in the US and challenged by the senator on the cost of this large thing. And the guy's sort of saying, "Oh, I understand the purpose is for fundamental high energy research and it's educational and academic." And Wilson points out that yes, and it's a cultural activity, but with the firm expectation that technological developments will come. And this is the first half of his quote, which a lot of people haven't heard before, which is just that because we are doing extremely difficult technical things and because we're working in a strange kind of research, we know from past experience that new techniques inevitably develop, techniques which have paid more than paid for the cost of the basic research that was not pointed to such developments. But that's only the first half of his response, right? So it's true. Like, and a lot of what I point out in the book are these stories of these unexpected spin-offs and the things that have come from the development of particle physics in ways that most people don't realize are connected, the development of our modern technology in our modern world, along with this curiosity-driven research. But it goes deeper than this, right? I think if we were to sell basic research based on its technological spin-offs only, we'd be selling it short. Because as Wilson said first, it's also a cultural activity, right? So he's challenged on this, and he says, he's asked whether or not the machine will have anything to do with the security of the country, which in the US is just such a phrase that I hear a lot, right? And Wilson just says, no. Now, he's a pacifist who worked on the Manhattan Project, right? That's his background. And the guy pushes him on it, and he just says, nothing at all. And Wilson knocks it out the park. Here's what he says. He says, "It has only to do with the respect with which we regard one another, the dignity of man, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in this country and are patriotic about. It has nothing to do directly with defending our country except to make it worth defending."
Yeah, that's beautiful.
Isn't that beautiful?
Yeah, that's great. Yeah. Yeah, it'd be like asking, what's the point of Shakespeare? Whoa.
Right. What's
Yeah,
the point of art? What's the point of music?
If you have to ask, then you don't get it. Right. Yeah, interesting. All right, Susie, we've been going an hour and a half. Let's shift to actually, before we shift to the lightning round, just take us back to, say, 1890s, what the understanding of the atom was, and then kind of do a quick tour. What happened? Right.
Whoa.
Back in the days when they said, "Oh, we're pretty much done with physics now. We just have to refine the, sixth
Right.
decimal point."
Yeah.
Yeah.
So we start at this point at the end of, near the end of the 19th century. People think physics is done. They have the basics of gravity. They sort of have known since the Greeks of this idea of atoms, but no one could explain things like how the sun could shine, or even in terms of relativity, some of the aspects of how the solar system worked even. And then over 120 years, we get to this point where, atoms are no longer solid. The particles within atoms have substructure. There are many, many types of particles, matter and light and all these things, well beyond what we even find in atoms. Everything changes over time, right? And the universe is actually, a chaotic, wild, violent explosion of a place that we happen to find ourselves in this sort of neat little neighborhood in which we can survive. It's just such a wild ride over 120 years, and it has completely changed our view of literally everything around us.
Yeah. Well, your book beautifully captures all that. So the ancient Greek idea of the atom is just literally atom, unable to cut any further. This is the smallest
object.
Oh, but that's gone out the window, right there. At the bottom, It's just pure energy. Or how would you say it?
That's a reasonable way to put it. Yeah. Yeah.
So what's string theory then trying to do? And what's the status of that these days, do you think?
Oh, goodness. So as an experimentalist, the status is it's one idea of many ideas that I wish I could test.
Okay. Right. There was that book a few years ago, Not Even Wrong, about string theory. I forget the author's name. It was one of the big string theorists that said, you know what, if we can't ultimately at some point test this, what are we doing?
Yeah. Yep. There are many beautiful ideas out there. And I think we're in an interesting phase of the experimental program, especially with the Large Hadron Collider, where those theories and ideas are actually being ruled out at a rate that we haven't seen for many decades. So I think hold that question for 10, 20 years, and we might be in a very different place, because we're going to have to go back to the drawing board and think again about how the universe works.
I always like to ask my guests, would you like to come back 500 years from be chronically frozen and then de-thawed 500 years from now? You come back and think, oh, that's so obvious. We should have known that. All those people back in 2022, look at the stupid things they believed.
It's going to be like that. Yeah. Yeah.
Okay, quick, a few things here. The Higgs boson. Just explain, what is this?
So as we understand it, it's the particle which sort of gives mass to other particles through. I would say through the equations is my caveat of that, right? It in itself doesn't play any direct role in our everyday matter, but this mechanism called the Higgs mechanism appears to be the way in which the universe works to actually generate mass, because the equations would be quite happy with no mass terms in there at all, or if all those mass terms were zero. And this mechanism in the mathematics actually creates the idea that the Higgs boson has mass. But the best analogy I found for how it works is a cocktail party. A rumor spreads through a cocktail party, and if you can imagine that, there's this rumor that's sort of spreading through the field. That's kind of what a Higgs boson is. It's like the rumor traveling through that causes this clumping of matter, and that clumping of matter is kind of how it generates mass. You said it's quick fire round, so that's a really, really too quick answer.
That's good. Okay, all right, what is gravity?
Good question. Not my area.
Okay.
Maybe ask a cosmologist.
Well, I just want to get past these kind of tautological definitions. Well, it's the tendency for objects to be attracted to each other. Why are objects attracted to one another? Gravity.
Yeah. I mean, I could give you that, but it's a circular argument, right?
Yeah. Right. I did ask Kip that, and he had an explanation having to do with time that I can't honestly say I really understood. Really, I think sometimes you really have to know the math, because
I mean, once upon a time I studied general relativity, but if you've got Kip Thorne on the line, I'd ask him.
Yeah, and same thing with time, right? It depends on what you're talking about or what experiment you're running.
Yeah, exactly. Yep, same question, and almost the the flip of the coin with something like mass would be what time is. Yeah, we don't even know how many dimensions we're in, really. So,
well, 4 dimensions we're in, at least.
Well, at least, see.
After that, I have no idea what I'm talking about.
I like to pretend it's just 4. It's fun.
Okay, why is there something rather than nothing?
Good question. The fact that we can even ask that question means there has to be something. So again, I feel we're into circular arguments. There may be universes in which there's nothing.
Yeah, but even that, see, if you define nothing as, I mean, really take everything away, there can't even be the concept of nothing.
Exactly.
Then I don't even know what we're talking about.
Exactly.
Right. So, right, I guess one answer is that maybe explanation just has to stop somewhere. It's Thomas Nagel, I think, called that one thought too many. Like he used that for consciousness. Just trying to explain it maybe doesn't need an explanation. It just is.
I always ask, like, is that the most interesting question we can ask about it? Why is it in the first place?
Right.
Yeah, I mean, a philosopher would make good progress based on that question, but as a physicist, I'm probably not going to make much progress based on that question. Yes. Personally.
Right. What do you do with it? Yeah.
Yeah. What do you do with it? Yeah.
It's fun to talk about over adult beverages, but.
Agreed.
All right. You must get asked the God question a lot. I have no idea if you're religious or not, or but people must ask you, given your profession, is there a place in your epistemology for a creator or God or anything like that?
Personally, I'm not a believer, but I do see a lot of value in religion, and I see a lot of value in holding that concept. So I'm almost on the fence. Like, I don't think there's the scientific pursuit of the ideas doesn't require that. And in fact, it probably muddies the waters a little bit to think about it in that way. But I think there's less of a dichotomy between belief and science than some people go for. Just like I said at the start, my sister and I were always asking these big questions about the universe, about how the world works. She was asking them through philosophy and history, and I was asking them through the sciences. One of us could easily as well have been asking them through religion. There are different ways of knowing, and there's different types of knowledge in this world. Scientific is one of them, and it's an extremely valuable and important one. But, there are other forms of knowledge, and I think those have value and shouldn't be maligned.
Like a little bit like Max Tegmark's idea, the universe is mathematical. Again, I'm not sure I really understand what that means. But maybe we're still playing word games, but math really exists, right? I mean, it's a real thing. We're discovering things about the universe and nature that can be described mathematically in that kind of language. But when someone like Max says, "Well, but the universe itself is mathematical," I wonder if that's just one thought too many in that category. Again, it's like what.
That's actually, I mean, it's a really interesting point. A lot of people have asked me in this book journey, when I go through this huge thing and I come to these big collaborations, and I actually interviewed a whole lot of colleagues towards the end of the book, mostly experimental colleagues, because that's what the book is about. But I chatted to a couple of theoretical colleagues as well. When I asked people what it was that we could learn from this whole journey of particle physics, I mean, most of the experimentalists came up, and it surprised me that they all came back with the same answer, which was we can learn how to collaborate, right? We can learn how to work together to do big things, which I completely agree with. It is a remarkable thing. But there was only one person who gave a different answer, and that was a theoretical physicist, a friend of mine. And what he said, what he thinks people should be able to take away from this whole adventure of understanding particle physics and the universe and its most fundamental nature is this idea that the universe is fundamentally knowable, right? That we can ask questions and actually get answers that are predictive, because at that base level, it seems to be, and it isn't necessarily. It wasn't necessary that this is how it works, but it seems to be that our universe is describable through mathematics. Now, I wouldn't go so far as to say our universe is mathematical, in terms of like maybe there are some things that can't be described through mathematics, but just about everything we've ever been able to see or test or understand can be described through mathematics. And that, if it is some sort of coincidence, is a remarkable coincidence, but it also just might be that, well, since mathematics is the only way we have of making a prediction, what else is there? And that's, I guess that's when you come to these other forms of knowing and other philosophies, including religions.
Yeah. I wonder if some of that would apply to the idea of the multiverse, whichever version you want to use. I guess yours for a particle acceleration, like that two-slit experiment thing, where as I understand it, the universe keeps dividing. There's an infinite number of universes. There's one out there just like this, almost like us, and you and I are having almost the same conversation, but not quite. Right? That, I don't know. To me, that just never passes muster. You look out the window, that doesn't look like what's going on in the world. So I don't know.
That's true, but I guess as a physicist, I've learned not to trust my everyday intuition, right?
Right. It's not accurate. No, not at that level. But the multiverse, what are your thoughts on that?
Oh, that's another really interesting one. I mean, there are people out there who argue that we already have multiverses because we each live in our own universe, right?
Oh, well, that's true, yes.
I mean, in a completely different context. But in the context that we usually understand in terms of theoretical physics and cosmology, fascinating concept. Again, could we ever come up with a way to test whether that hypothesis is true?
Right.
Potentially, like that's where it gets really interesting to me. Really interesting to me is like when we get to the point where we can start cleverly asking, okay, well, if this were true, this would come out this way, and then if this other thing were true, this would come out the other way, and then designing and building experiments to be able to test that. And
I thought
then
about
I'm
that
on board.
Otherwise, with gravitational waves, if there were other universes, other bubble universes colliding with ours, maybe they would leave a little ripple in the gravitational waves or some such thing.
Oh, perhaps. I'm sure someone has studied that. I'm sure there's papers out there on that, but I'm not across the literature. Yeah.
Right. Yes. All right. Okay. So you end your book talking about moving into your new lab there at Melbourne. What are you doing next? What's your next research project?
So the lab renovation is finally just finished. A few delays through COVID. So beautiful new lab there. So some of my current research projects involve trying to shrink down particle accelerators using new technologies that have come out of CERN in particular. We collaborate with CERN quite strongly to try and make smaller, lighter particle accelerators that can be used out in the field or in hospitals, and bring these techniques to places that previously were difficult to come by. The flip side of that is one is like cutting edge, right? The flip side of that is I'm also working with a collaboration called the Stellar Collaboration, which involves a bunch of people from mostly sub-Saharan African countries, but also other low and middle income countries, as well as experts from the US, the UK, and other high income countries to work together to try and improve the robustness of particle accelerators used for cancer treatment. So they're called linear accelerators, which is like a mainstay of cancer treatment. It's used in like 50% of all cancer cases where it's available. But this is like a sort of equity issue at the moment, which is that by 2035, 70% of all cancer cases are going to be in low and middle income countries. And our current technology is failing there more frequently than it fails in a high income environment for many, many complex reasons that the collaboration is digging into. So that's one that's really close to my heart, is trying to understand how to make the technologies that have come through this fundamental research and actually make them more accessible to do more good in the world.
Are these like gamma knives? My mom had brain tumors that she had zapped. Well, first of all, she had craniometries, but you can only open the skull so many times. So then they put this big helmet on that looked like one of these old like phrenology helmets,
Mm.
right? But I guess it was directed beams at just the little
Yeah.
tissue, right? So that's what you're getting better at doing.
Yeah, that's right. So
And the
the
problem is
slightly
those
larger
machines are
version.
super expensive.
Yeah, but well, the upfront cost is only one issue. It's actually being able to keep them running. Like imagine a car that just breaks down all the time, right? And trying to or like imagine, space technology where you send it off and you don't have the ability to fix it. Like I kind of call it the robustness frontier, right? Like trying to design things in such a way that they're not going to fail even when they're used day in, day out in a challenging way. Things like predictive maintenance and trying to understand which pieces break and why. And in the US or in Australia or in the UK, if a part of one of these machines breaks, you can get it same day delivery, right, from the factory. If you're in Ghana, it gets stuck in customs for 2 months and
Oh
you
my
can't
God.
treat, and there's 50 patients a day that aren't being treated, right? Because of that problem. That's only one small, tiny aspect
Wow.
of the problem.
Wow.
So yeah, we're really, we've worked for about 5 years now, in really listening mode, with the people who are on the ground doing the work, using these machines to try and understand exactly what is going wrong. And then, the next phase of that collaboration is moving towards then genuinely improving the technology for those applications. Yeah. I also do a bit of work in designing next generation sort of even more precise forms of cancer treatment using protons and carbon ions. And the US has quite a lot of proton therapy as well, but is just getting into the heavier ion. So I also go way back into the sort of the physics end of designing those machines to try and make those smaller and lighter and better suited to their applications as well. So I sort of cover the cancer treatment spectrum, but really way back in the associated technologies.
I just looked you up on Twitter before we came on, and the recent post you said something like 2022 was one of the best years and one of the worst years of my life, or whatever. But I didn't look down. Did you explain what the good and the bad were?
Oh, well, I mean, the book was great.
Yeah,
So it
the new lab.
came out in the UK. Oh, yes, a new lab, so much going on. It's been a great year. The downside is COVID stuff, basically. I'm almost 6 months into having long COVID at this point, and the fatigue associated with that. So that's been a real struggle. But again, in the long view, well, I'm like trying to go like, okay, where can I sign up for studies to at least donate my experience to science?
You don't seem like, you don't seem like you have brain fog or any of that. What are your symptoms?
No, brain fog's one of them.
You do?
Yeah.
I certainly didn't notice it.
Oh, I'm grateful. There were 2 coffees before we went to record.
Oh, I see.
But so I'm still taking like multiple naps a day to try and even out my energy levels. But I've got a team now supporting me in that and working through the fatigue and as long as I rest properly, then the brain fog's not so bad.
I see.
Yeah. But if I tried to do a second interview now, I'd be like, oh no.
Oh, okay. Right. All right.
Yeah. So that's been challenging.
All right, Susie, you are a gifted writer. I really enjoyed your book. What's your next popular book project you might work on?
I think you might have got a hint from some of the stories I was telling about some of the women.
Yeah.
So one of the amazing things that happened in writing this book, first of all, is just finding all those stories. But now I get contacted by people whose relatives or mother-in-law, made some discovery or did something. So there's something in that space, I feel, that which is where I want to go next. Is
I like that.
It's these stories of women, and I'm not there yet with it. And if anyone out there who's listening has a story that's never been told of a woman who's worked, especially in physics, I'd love to hear it. So pop me an email. My contact details are on my website.
I'll put that in our show notes. Yeah. You should do a documentary film on Rutherford's grad student. What was her name again?
Harriet Brooks is her name.
Harriet Brooks. Yeah, that's a great story.
Happy to present a doco on that.
Yeah, you should. Absolutely, you should. That'd be great. All right, Susie, thanks so much. That's a good place to end it. Thanks for talking to me.
Thanks, Michael.